In this series of videos, we're going to be exploring potential energy, the opposite type of energy as kinetic energy. The relationship between these two types of energy can be seen in this equation here, where the sum of all kinetic energy in a chemical reaction system plus the sum of all potential energy in a chemical reaction system add together to give us E sub T, which is the short form for thermal energy, more commonly known as enthalpy, which we represent with the term H. If we break this down, what this equation shows us is that if thermal energy remains constant, which would happen if the temperature and pressure of a reaction system also remain constant, that means that an increase in potential energy would consequently mean a decrease in kinetic energy in order for this equation to be true, thus showing that kinetic and potential energy have an inverse relationship with each other. If we break down what the term enthalpy literally means, enthalpy is a measurement of the total energy that is stored within the bonds of all compounds within a reaction system, which is what potential energy is, added to the total energy of movement of those particles within a reaction system, which is what kinetic energy is. However, enthalpy on its own, thermal energy, is relatively uninteresting to study because of the fact that it remains constant. What is more interesting and useful to study is the change in enthalpy that occurs between the kinetic and potential energy of the reaction system itself, because this tells us the overall progression of how the reaction works. Therefore, instead of referring to the variable H, we use the variable delta H to represent the change that takes place between kinetic and potential energy. And we represent delta H with the formula potential energy of all products within a reaction system, from which we subtract the potential energy of all reactants within a reaction system. Another way of looking at this is the change in potential energy in the reactants to when they become products. So as a consequence of looking at the delta H formula like this, delta H can also be used to represent the change in potential energy between reactants and products, although we can just as easily write this formula relating to kinetic energy instead. In terms of numerical conventions, if delta H is greater than 0, or if delta H, the actual energy term, is written in the reactants of a chemical reaction, the reaction is defined as being endothermic. Conversely, if delta H is written as being less than 0, meaning that delta H is negative, or if delta H is actually written in the products of a chemical reaction, the reaction is known as an exothermic reaction. The etymological roots, the actual meaning of these words, will be explored in more detail when we actually look at a few chemical equations. So here, if we take a look at these chemical equations, we can actually see that these equations have energy terms in kilojoules listed in either the products or the reactants. So in this case, remember that if energy is a product in the equation, that means that our reaction is exothermic. In other words, exo is a prefix that means outside, which means that this energy term here is a product, which means that this reaction here produces energy. Hence why the energy is found outside of the reaction, because it is released by the reaction as it occurs. And the actual value of delta H here, remember that delta H, if energy is released, is written as a negative number here, so we would say that delta H is equal to negative 1,371 kilojoules per mole of the reaction. Conversely, this reaction here, the synthesis of nitrogen monoxide, we see that delta H is actually a reactant, which means that this reaction consumes energy. What this means is that in order for this reaction to occur, we would need to add 180.5 kilojoules per mole in order for this reaction to successfully occur. And because delta H is in the reactants, we define this as an endothermic reaction. Endo is a prefix that means within, because the energy is used by the reaction instead of being produced. And according to the numerical conventions, because delta H is a reactant here, we would define delta H as being positive. So our delta H term here would be positive 180.5 kilojoules per mole. And from there, you can use these equations below to practice identifying whether an equation releases energy or whether it consumes energy, and identifying the direction of delta H, whether it is negative when the reaction produces energy or positive when it consumes energy. So in closing, what actually determines whether a reaction consumes energy or whether it produces energy? Well, all of the energy that goes into a reaction, so all of the energy that is added to a reaction, is used to break the bonds or reshuffle the bonds around within the reactant. So again, this is energy that is absorbed. And then energy that is released by a reaction is released whenever the bonds are reformed in order to make the products. And if any extra energy that was put in is left over, that extra energy, which is what we call the energy output, is then released. So therefore, the difference between the energy input, the energy absorbed, and the energy output is what determines whether the reaction either releases energy if the reaction is exothermic, or if the reaction absorbs energy where it is endothermic. There are a few general trends that we can look at in terms of predicting whether reactions release energy or consume energy. For example, our top reaction is a combustion reaction, and we know that combustion reactions always produce a large amount of heat, but certain other reactions, like the two synthesis reactions here, are both endothermic, whereas the synthesis reaction below is exothermic. So generally, determining whether a reaction is exothermic or endothermic can almost only be done using actual experimentation and measuring any change in temperature that occurs because of the reaction. In the next video, we're going to explore how to represent exothermic and endothermic reactions graphically in order to understand this convention about why endothermic reactions have a positive delta H and why exothermic reactions have a negative delta H.